Hello and welcome to the chapter 14.2 lecture on calculus of vector valued functions. Before we begin, I want to point out that at the end of this lecture, we go through this 14.1 problem proving that this vector function lies on a sphere, which is historically one of the most missed or struggled with problems. So you're welcome to skip ahead if you want to see that first. So recall tangent lines from calculus 1. Now we generalize that to tangent vectors of curves in higher dimensional spaces. So given a vector valued function r of t, a tangent vector to the curve at a particular point is defined as the limit as delta t approaches 0 of the change in position over the change in time, also known as d dt of r of t. Here's an illustration of that. So we have r of t going to a point P, and r of t plus delta t, a little change in time, and then it's pointing to a different point Q on the curve. And that change, as you can see, is approximately tangent to the curve, and as delta t gets smaller and smaller, then it will be an exactly tangent to the curve. So we have delta r over delta t as a tangent vector to the curve. Here's an illustration of it getting closer and closer and resulting in what we call r prime of t, which is a synonym for d dt of r of t. And fortunately, computing this is relatively simple, at least given calculus 1. The derivative of jeez. The derivative of a vector valued function is fortunately just the derivatives of the component parts in the calculus 1 sense, provided that the resulting vector is not 0. After all, if the resulting vector is the 0 vector, then, well, the 0 vector doesn't have a direction, so that it would not be a tangent vector. We'll see some examples of this in a bit. And here's the proof of it. So rigorously, r prime of t is the limit as delta t approaches 0 of r of t plus delta t minus r of t over delta t. This is the exact same definition of a limit from calculus 1, except now with vector functions as the functions. And that can be expanded in this way. We expand it in terms of the components, gather their respective components, so gather the I component, j component, and k component, and look what emerges. Each component is just the calculus 1 definition of the derivative of that respective component. So, for example, let's find a tangent vector to the circle, which, as we saw in chapter 14.1, is parameterized by cosine ti plus sine tj. Recall that that came from this picture. That's a right angle, and this guy is cosine of t, and this vertical part, the opposite, is sine of t. And that's the x and y components respectively, hence our standard parameterization of the unit circle. Okay, so r of t has these components cosine of t, comma sine of t, and r prime of t is just the, or contains the derivatives of the respective components. So d dt of cosine t, d dt of sine t, and that is negative sine of t comma cosine of t. So that's a general tangent vector. And then in this particular case, when t is pi over 3, for example, we just plug that in. And a tangent vector at that point would be, okay, plugging in, we have that. Sine of pi over 3 is root 3 over 2. So we have negative root 3 over 2, comma 1/2. So that would be a vector that looks like this, color coding. Okay, we saw this helix in chapter 14.1 as well, and proved that, for example, its projection onto the xy plane is an ellipse, and then it's moving up 1 unit every rotation. Here, a tangent vector, so once again, just taking the derivatives of the components. Okay, derivative of 4 cosine t is negative 4 sine t. Derivative of sine t is cosine t, and derivative of t over 2 pi is just 1 over 2 pi. And when t is 2 pi, okay, well, sine of 2 pi is 0, cosine of 2 pi is 1, and this stays 1 over 2 pi. Okay, and the point 2 pi, that means that we have done 1 revolution, and we are right there. There, that x direction, that y direction is the green, and that red direction is the z. Differences. Now, we call a vector function smooth on an interval if that vector function is differentiable on that interval, and r prime of t is nowhere the 0 vector on that interval. Remember that 0 vector doesn't have a direction, so it doesn't make sense to say that, well, it has a tangent vector there, at least with the given parameterization. So here's a non-example. By non-example, we mean something that is not smooth. So consider r of t is t cubed I plus t to the 6j. First, what does that parameterize? What does the curve look like? So this is, as in chapter 14.1, that's the x-coordinate, that's the y-coordinate. Can we find a relationship between them? Well, y, that's t to the 6, which is t cubed squared, but t cubed is x. That's our x. Okay, so this parameterizes the curve, y equals x squared, a parabola. Now, what's interesting here is a parabola clearly has a tangent vector at 0. However, if we take the derivative of r of t, so r prime of t, that would be d dt t cubed, comma d dt of t to the 6, which is 3t squared, comma 6t to the 5, and then r prime of 0, which is this point, would be just plugging in 0, 0, comma 0, which is the 0 vector, and that means that it is not differentiable here. Well, it is differentiable at 0, but it's not smooth here. So the point of this example is to illustrate that even if the curve may have a tangent vector, r prime of t may not meaningfully give it. However, a reparameterization would. And we can, quote, fix it by reparameterizing. So for example, letting s be t cubed, then that's now s, and this is s squared. That's because t to the 6 is again t cubed squared, which is s squared. Okay, now this new parameterization is such that now r prime of s, that's d dt of s, comma d dt of s squared, and that is 1 comma 2s, and now r prime of 0 plugging in is 1 comma 0, and now it is, as we call it, smooth here, since it's differentiable, and now the canonical tangent vector is not a 0 vector. And indeed, this vector here, let's go back to our graph of the parabola. That's our y equals x squared. 1 comma 0 looks like that. And that is indeed a tangent vector right there. X coordinate, y coordinate. So while some curves can be, quote, fixed by reparameterization to make them smooth, not all curves can be. So a curve with a cusp, here's an example, cannot be reparameterized in any sense to make it smooth there because it's not differentiable there in a fundamental sense. In the same way that, well, actually this is a calc 1 function on the x, or it looks like a calc 1 function on the xy plane with a cusp, and recall from calc 1 that cusps have no derivative there because, well, there are kind of many different tangent things, different tangent lines. It can swivel, and there's no meaningful sense in which there is a tangent line there. So this is fundamentally not smooth even under any reparameterization at 0. Now, tangent vectors in the sense that we just gave can be of kind of an arbitrary length depending upon the nature of r of t. And we're often interested in just a pure direction in which the curve is moving. And that pure direction would be a unit tangent vector, meaning a tangent vector of length 1. But we know how to make any vector into a unit vector. We just take that vector and scale it back by its length, and scaling it back by its length makes it of magnitude 1. So the unit tangent vector, we denote it with this boldface t at a particular time or parameter value, little t, is given by this. A tangent vector divided by its magnitude to make it a unit. So here's an illustration of a bunch of little unit vectors. You can see they're all of the same length for this curve, this vector function. So let's do an example. Find the unit tangent vector to this curve. It's the same one illustrated over here at t equals 1. Okay, same problem. Okay, so we know that, well, r prime of t, that's the derivative of each respective component. And derivative of t squared is 2t, derivative of 4t is 4, and derivative of natural log of t, recall, is 1 over t. So this will be 4 times 1 over t is 4 over t. Okay, now r prime of 1, the point at which we want to find the unit tangent vector. And I know this is not the unit tangent vector yet. We're just finding a tangent vector here. Would be 2, 4, 4, plugging in 1. And now the unit tangent vector there would be r prime of 1 over the magnitude of r prime of 1 to scale it back and make it of unit length. So that's 2, 4, 4. And its magnitude is the square root of the sum of the squares of its components, as we know. Okay, and that's 4 plus 16 is 36. And the square root of 36 is 6. So a unit tangent vector there is 1/3, 2/3, 2/3. Distributing that 6. And we're often interested in the general unit tangent vector to a particular curve. We'll do things like take the derivative of the unitary tangent vector, and that will be a very meaningful concept. So the general unit tangent vector, so we already know that r prime of t is 2t 4 over t. And then the general unit tangent vector is r prime of t over the magnitude of r prime of t. And that magnitude is, as always, the square root of the sum of squares of its components. So we have 2t squared plus 4 squared plus 4 over t squared, and the square root of that whole thing. Now, this is perfectly fine in a sense. I mean, this is completely correct, and it does give an expression for the unit tangent vector at any point t. So the illustration is here, just plug in a point t, little t, and you get the unit tangent vector there. However, we can algebraically simplify that, and obviously if we want to take the derivative of something like the unit tangent vector, this is a mess. So the point of the following will be to show, well, an algebraic simplification. So first, let's compute that denominator. And we'll simplify this and we'll show that we can get it out of the square root. As you know, square roots and derivatives are annoying. Okay, so that's the square root of 4t squared plus 16 plus 4 squared over t squared. Now, if we want to get it out of the square root, well, sometimes we can't do it, but in this case, we actually can. So notice that we have this denominator of t squared. Let's make it so that everything has a denominator of t squared. So how can we make 4t squared have a denominator of t squared? We can multiply it by t squared over t squared, which is a fancy form of multiplying by 1. Let me illustrate. So that's 4t to the 4th over t squared. This guy, of course, t to the 4th over t squared is t squared. So that's the same as that. Similarly, plus 16 t squared over t squared. And this guy we leave as is. The point is now they have a common denominator. Okay, so we have 4t squared plus 4t to the 4th plus 16t squared plus 16 all over t squared. Okay, square root of t squared, that's absolute value of t, or just t if we're always positive. That's nice. And the numerator here, maybe if we can write it as something squared, then, well, we can take the square root cleanly. So I'm going to need to erase this, but it will continue from here. So far we had that denominator was the square root of 4t to the fourth plus 16t squared plus 16 all over t squared. And that numerator is in fact 2t squared plus 4, all squared. Take a moment and FOIL this out, and you can confirm that it is indeed that numerator. Okay, now we have the square root of squares, and those cancel out, and we just have 2t squared plus 4 over t squared. And technically, that's if t is positive, else it's the negative of this. Because technically the square root of a square is the magnitude. That is the absolute value. And the absolute value of a negative number is the negative of that negative number to make it positive. Okay, but for simplicity, let's do that. And often in practice, that will be the case. Okay, and that's the same as 2 plus 4 over t squared. Okay, that's nice. That's a very nice expression for the magnitude, the general magnitude at any t. Okay, so now that general unit tangent vector, so recall it was r of t over the magnitude, r prime of t over the magnitude, that was 2t comma 4 comma 4 over t over the magnitude, and now the magnitude we have found is 2 plus 4 over t squared. This guy here is the magnitude of r prime of t, and this denominator is just r prime of t. A tangent vector over its magnitude to make it a unit. T of t. Okay, so the general unit tangent vector at a point on this curve, any point at all, is 2t over 2 plus 4 over t squared, comma, 4 over 2 plus 4 over t squared, comma, 4 over t over that is 4 over t times 2 plus 4 over t squared. You may be thinking, okay, that's still ugly, but it's way prettier and way easier to do derivatives with than the square root of a polynomial with a quotient in it, etc. And this can still be algebraically simplified a good deal, and it's not bad to compute these derivatives, knowing Calc 1. If we wanted to take the derivative of the unit tangent vector, which we may want to do, will want to do in the future. Now, so we have learned about derivatives of vector-valued functions, and these derivatives obey all of the same rules, really, as Calculus 1 derivatives. And in Calculus 1, you had a notion of product and the product rule. Well, now with vectors, we have two types of products, the dot product and the cross product. And both of those obey the product rule, amazingly enough, which is part of the way in which they are intrinsic notions of products on vectors. So first, the derivative of a constant vector. Remember that all of these bold things are actually vectors, not scalars. So the derivative of a constant vector is 0. After all, constant vector, that means that every component is a constant. So the derivative of each component is going to be 0. The derivative of a sum of vectors is the sum of the derivatives of those vectors. For similar rules or similar reasons, just think of it component-wise. Now, the product rule is still obeyed, and the chain rule is still obeyed. Obeyed in the sense of generalizing from Calc 1. So a vector function of f of t, notice the difference between the bold script here and the not bold script for f. That means that f of t is a function from the real numbers to the real numbers, while u of it outputs a vector given this real number. And it obeys the product rule that it's u prime of f of t times f prime of t. Sorry, chain rule. I just mixed up what I verbally said. It obeys the chain rule that is the case. And remember the product rule that the derivative of f times g is f prime g plus fg prime. Well, the dot product is a type of product and it obeys that product rule. ddt of u dot v is u prime dot v plus u dot v prime. And same with the cross product. ddt of u cross v is the same thing, but now with the cross product. So, very convenient. For the sake of illustrating, I'll show the proof of the dot product rule, and other proofs are very similar. So ddt of u dot v, well, if u has components u1, u2, u3, and v has components v1, v2, v3, then the dot product is just u1 times v1 plus u2 times v2 plus u3 times v3, denoted here. And the derivative of that, we apply the ordinary product rule on each part, and then gather together all the terms with derivatives of the first components, and gather together all the terms with derivatives of the second components, and realize that those are themselves dot products. And hence the result is u prime dot v, which is this guy, plus u dot v prime, which is the sum of these three terms. Yeah, so point is, break it up into components and apply calculus 1 rules, and then gather terms appropriately, and you can prove all 6 of these. So just to illustrate, let's use the chain rule, generalized to vector functions, to find ddt of r of sine of t. For r of t, this same vector valued function that we just dealt with and found the general unit tangent vector for. Okay, so r prime of sine of t got ahead of myself. ddt of r of sine of t is, by the chain rule, r prime of sine of t times, well, sine of t prime. This is our f prime of g times g prime, the ordinary product rule, but now it applies, as we know, to vector valued functions. Okay, so we know that r prime of t, taking the derivative of r of t, is 2t 4 over t, as we found earlier, and as you can re-verify. And the derivative of sine of t is just cosine of t, as we know. So d dt of r of sine of t is, okay, so plugging sine of t into this. So now sine of t goes where all the t's are. We have 2 sine of t, comma 4, comma 4 over sine of t. And then this cosine t is still hanging out on the outside. So times cosine of t. And cosine of t is a scalar. In a sense, it's just a real number. And we can distribute that to all components. So we have 2 sine of t cosine of t, comma 4 cosine of t, comma 4 times cosine of t over sine of t. And if we want, we can simplify that by knowing that, for example, cosine over sine is cotangent. And this guy, it's a identity, a double angle identity, that this is sine of 2t, which is a much nicer expression. Okay, and we know that this guy is cotangent of t. So this is sine of 2t, comma 4 cosine of t, comma 4 cotangent of t. Is the derivative of r of sine of t using the chain rule and this trig identity, double angle identity. In this class, it's useful to know the double angle identities in general, as we saw in chapter 14.1. Okay, and we can also take higher order derivatives, and this just means applying the derivative twice, same as in Calc 1. So d squared dt squared of r of t, that just means d dt of d dt of r of t. Okay, d dt of r of t is 2t for 4 over t, derivative of each component. And now we take the derivative of each component again. And we have 2, 0, negative 4 over t squared. So that's derivatives of vector valued functions. And we can also take integrals, both indefinite and definite. So first, an indefinite integral of a vector valued function, little r of t with these components, f, g, and h, is big R of t with components big F, big G, and big H, such that the big f, g, and h are antiderivatives of the little f, g, and h. Antiderivatives in the calculus 1 sense. So then the indefinite integral of little r, denoted with our usual integration notation, is big R of t plus c. We always have to add an arbitrary constant. And we should note that, as usual, all of these are vectors. So this constant vector has components c1, c2, c3, each of which is a constant. And this is the general antiderivative of little r, in the sense that if you take the derivative of this, then you get back little r. And we can also take definite integrals. So if the components are integrable on a region, a to b, Then the definite integral on that region is the integral from a to b of r of t dt, and that is defined as the integral from a to b of the first component dt, I, denoting it's still the first component of the vector, plus the integral from a to b of the second component dt, j, denoting it's the component of the second vector, or second coordinate of the vector, etc. So let's do an example. The indefinite integral of 1 t squared dt is integral of 1 dt, comma, integral of t dt, comma, integral of t squared dt is t plus an arbitrary constant, c1, comma, 1/2 t squared, plus an arbitrary constant, c2, comma, 1/3 t cubed, plus an arbitrary constant, c3, and that's t 1/2 t squared, 1/3 t cubed, plus c1, c2, c3. And this whole guy, we can just denote it as big C, a constant vector. And that's how we typically do it. And I just did this to illustrate where that constant vector comes from in terms of the individual antiderivatives. Okay, and then the integral from 0 to 1 of this is the integral from 0 to 1 of t dt, or rather 1 dt, the first component, integral from 0 to 1 of t dt, and 0 to 1 of t squared dt. And we all know how to take definite integrals of functions like this, and that is 1, comma, 1/2, comma, 1/3. If you're not sure where these came from, definitely review your definite integrals from Calc 1. Alternatively, we can write that this definite integral is the indefinite integral that we found, evaluated between 0 and 1. So our indefinite integral was this, okay, plus an arbitrary vector, and we're evaluating that between 0 and 1. Okay, so plugging in 1, we have 1, comma, 1/2, comma, 1/3, plus our arbitrary constant, minus, plugging in 0, we have 0, 0, 0, plus our arbitrary constant, and the arbitrary constants go away, and the vector difference, we're just subtracting 0, so that is 1, oh my gosh, 1/2, 1/3. The second way will be our preferred way moving on in the class, just because it is in terms of vectors themselves and kind of a more general way to think about it. Now, what's the utility of vector derivatives and integrals? Well, the derivative of velocity is acceleration. Recall this from Calc 1 or 2. The derivative of velocity is acceleration. And same thing applies with vectors. Okay, and the derivative of position, well, change in position over change in time is the velocity. We typically denote position with s. So that's the velocity. Okay, so part A, we know that acceleration is the derivative of velocity. Okay, that's d dt of 2I plus t squared j plus 4tk. And we just take the derivative of each component. I mean, this is a vector, and the derivative is the derivative of each component. And that is 0I plus 2tj plus 4k. And in this notation, I should note, we often omit zeros. So we would often denote or write this as just 2tj plus 4k. And that's the same as 0, 2t, 4 in our other notation. Now, it's displacement. So what is the difference in position of the particle given its velocity vector? Well, we know that that velocity is the change in position per change of time. So dds of s of t is v of t. And that means that integrating both sides, that the position is the integral of velocity. Okay, now taking the indefinite integral, we'll have that arbitrary constant. And that's because given the velocity, we don't actually know where the particle begins. If it's, yeah. However, we can still find the displacement. Because in the displacement, that's a difference in position, and a difference in position, the arbitrary constants will cancel out. So the displacement here will be between t equals 0 and t equals 3, will be the integral from 0 to 3 of v of t dt. So this is what we need to evaluate to find the displacement of the particle between those two times. Let me draw a picture. Okay, so here is our particle. Let's suppose that it moves like this. Okay, so purple is the particle and blue is the path that it moves. Then the displacement is this vector, the yellow one. So that's what we're finding. We're finding that displacement vector showing where it moved to relative to its initial position. Okay, and that is this integral. That is the integral from 0 to 3 of 2 comma t squared comma 4t dt. And that is integrating each component. This vector evaluated between 0 and 3. Okay, at 3, that is 6. Okay, and remember that the plus c's will cancel out, so there's no need to write them. So there's no need to write for definite integrals. Okay, so plugging in 3, 2 times 3 is 6, 1/3 times t cubed is 9, and 2 times t squared is 18. And plugging in 0, everything is 0. So we just have 6, 9, 18 is that displacement vector between t equals 0 and t equals 3. Okay, and going back to my comment that given the velocity, we don't know its initial position, so that's why we have the arbitrary constant kind of corresponding to the initial position in the position vector generated by the indefinite integral of the velocity. However, if we know the position at a particular time, then we can find its position vector as a function of time from the velocity and that position at a particular time. Okay, so we know that the indefinite integral, that s, the position, is the indefinite integral of the velocity. So integral of 2t squared 4t. And with indefinite integrals, we do need to keep track of that arbitrary constant. So that's 2t 1/3 t cubed, 2t squared, plus some constant vector. Okay, but now we can solve for that constant vector, given that the position at time t equals 1 is 1, 2, 3. So now we also know that the position at time t equals 1 is 1, 2, 3. So we plug that in to this, including that constant, and we'll solve for the constant vector. So what do we get? Well, s of 1, plugging in, we have 2, 1/3, 2, plus our arbitrary constant vector. This time let's write out the components, c1, c2, c3, must be equal to 1, 2, 3. So look at that. Now equating coefficients, we know that 2 plus c1 must be equal to 1. First component adding these vectors together is the first component of the right-hand side. The second components must be equal, so 1/3 plus c2 must be equal to 2, and 2 plus c3 must be equal to 3. So we know that c1 is -1. We know that c2 is 2 minus 1/3 is 5/3. And we know that c3 is 1. So we have thus solved that the general position vector. Okay, so plugging these back in over here, over here rather, our general position vector, that is 2t minus 1, comma, 1/3 t cubed plus 5/3, comma, 2t squared plus 1. Okay, so again, that was plugging the C1, C2, C3 into our general form for the position vector. So that was 2t plus C1, where C1 was minus 1, so 2t minus 1, adding these together, 1/3 t squared. The second component of big C was 5/3, so 1/3 t squared plus 5/3, and 2t squared plus the third component of big C, which was C3, which was 1. So 2t squared plus 1. Okay, and that concludes actually our chapter 14.2 lecture. And now I think it might be a good idea to go over one of the most missed or struggled with homework problems from 14.1. So in 14.1, we learned how to find surfaces on which parameterized curves lie. And this homework problem was to prove that this R of t lies on the surface of the sphere centered at the origin. So first, a sphere centered at the origin, that means it's of the form x squared plus y squared plus z squared equals r squared. And this first component here is x, the second component is y, and the third component is z. So that means that we want to show that x squared plus y squared plus z squared equals r squared, or r some constant. So that tells us exactly what we want to do. We want to take this guy, the x squared, add it to y squared, add it to z squared, and then use trig identities to hopefully get a constant. However, in the current form, that looks like it'll be difficult because we have like a cosine 2t and a cosine of t, a sine 2t. So let's first get everything in terms of just sine and cosine of t alone. No 2t's inside the trigonometric functions. So what do we know? Well, we know it tells us over here that cosine of 2t is 1 minus 2 sine squared t. This is one of the three equivalent forms of the cosine double angle identity. And the other double angle identity that we should know, memorize this, is that sine of 2t is 2 sine t cosine t. We used this, in fact, earlier in this lecture. So re-expressing our x, y, and z in terms of just sine and cosine of t, well, x is 1/2 sine of 2t, which is 1/2 times 2 sine t cosine t, which is just sine t cosine t. Okay, that's nice. Okay, and the y component, that's 1/2 1 minus cosine 2t. And again, we want that just in terms of sine t and cosine t. And the problem gave us this double angle identity for 2 theta. So plugging that in, we have 1/2 times 1 minus. This guy is 1 minus 2 sine squared t. Okay, fortunately, 1 minus 1 goes away, and then we have minus 2 sine t. And 1/2 times 2 sine squared t is just sine squared t. Okay, how pleasant. And z is already pleasant. Z is just cosine of t. Okay, so therefore we want to show that, well, x squared plus y squared plus z squared is a constant, and that's now sine t cosine t squared. Okay, and we wanted to show that x squared plus y squared plus z squared was a constant. So now that becomes, well, this is now our x squared plus our y squared is sine squared of t. And we want to square that as well. That is our y squared. Okay, then plus our z squared. That's plus cosine of t squared. And we want to show that that is equal to r squared, where r squared is a constant. Okay, so now this problem reduces to using some trig identities and hopefully getting that this whole thing is constant. It looks like we'll probably need to use sine squared plus cosine squared as 1. Okay, so that's sine squared t cosine squared t, distributing the squaring. Sine squared squared is sine. I'll actually write it this way. I'm writing it this way to have sine squareds, and that way it'll be more clear that if we have a sine squared plus cosine squared. And over here we have cosine squared of t. Okay, now, right now we don't have any sine squared plus cosine squared. However, look at this. Both of these guys have a sine squared. And if we factor out that sine squared, then what's left is a cosine squared plus sine squared. So let's write this now as sine squared t times cosine squared plus sine squared. Oh, look at that. This guy equals 1 by the Pythagorean identity. Sine squared plus cosine squared is 1. Plus cosine squared t, still there. Okay, so because that's 1, that's sine squared plus, okay, now we have this guy is cosine squared. Okay, but once again, sine squared plus cosine squared equals 1. Okay, so that's 1. And 1 is 1 squared if we want to write it that way, to make clear that it's the r squared.